So my 2025 started with an on-call page. We were just back from New Year's. Everyone was still in the holiday mood. And my teams got a page that there was an outage in one of our cells. Latency had gone up 10x. Search requests were timing out. And traffic was getting mitigated to other cells, which is, our normal mitigation strategy. Now, we do run a very well-oiled machine, but we had this issue, and everything seemed normal. There was apparently nothing was wrong with the cluster. And while we were still trying to figure out what is wrong, gather all the metrics, the issue auto-recovered. Now, this would happen multiple times over the next few months. And while this is not the worst outage I have seen, I have friends here, you're all working with cloud services, and you've seen worse outages. Folks at AWS here would know. The issue here was serious. We had a ghost in our system. We didn't know when it would strike. We didn't know what was causing it. And we really didn't know what we should do to prepare for it. My story today is our story of chasing this ghost. And our pursuit led us through, we started with search, then it led us through indexing. We went down replication, and then we went to operating system fundamentals. And we've learned some lessons along the way. I think folks here who run large-scale replicated search engines could benefit from it. So that's what I'm here to share with you all. My name is Vigya Sharma. I'm a principal engineer at Search in Amazon. And my teams are responsible for search on the e-commerce platform. So anything you search on Amazon.com, Prime Video, the search engine that runs search on the retail business. I'm also a committer and a PMC member on the Apache Lucene project. And before I joined the e-commerce search team, I worked in AWS and I worked with the OpenSearch team there. So I worked there for 7 years. I made a lot of great friends, did some really cool, learned a lot, really, built some cool stuff. So the OpenSearch project and the community is really close to my heart. And I met a lot of friends here. It's really good to see you people. I've seen some of you in forums, though we've never met personally. It's really nice to be here, so thanks for having me here. Back to the ghost. Now, I apologize, the graphs don't have axes, but what we really care about and what I want to walk you through today is relative values and impact. So like I said, we would get these pages, we would get these issues. Latency would suddenly spike up. Search requests would start timing out. We had to route traffic out of the cells into different healthy cells. And we collect a lot of metrics. We own the search service. We own it end to end. So we know exactly the kind of traffic and the kind of clients we work with. There were no rogue clients who were making extra calls. There was no sudden burst in search traffic. There was no bad deployments. We look at latency across different phases. There was nothing wrong in any specific search phase. It had just gone up across the board. All the usual issues. We looked at JVM, we looked at garbage collection, everything was working fine. So what gives, right? If something is wrong, something's not working, it gets broken every time. What's really happening with the system? Now, as a lot of you who work closely in operations would already know, if there's nothing wrong in your corner of the service, if there's nothing wrong in your process, you start looking deeper. You start looking at the lower layer. So you look at JVM, JVM is fine. Then you look at operating system. You start digging deep into what metrics are going wrong. Now, another thing you should know is we run hot indexes. We are a search-specific use case. We want minimal latency. And so all of our indexes are hot. They're supposed to be RAM resident. We even warm them up to load them in memory. And what we observed is whenever these outages would happen, we would see a surge of major page faults. Something was happening in the process which should not have happened, and a lot of pages were being loaded in memory. In fact, to give you an idea, this is another graph. This is what those things would look like. And as we kept digging deeper and digging for clues, we found another weird correlation. Each of these major page fault spikes would coincide with an increase in the size of our replication payload. So whenever the size of our checkpoint payload increased, we saw a lot of major page faults. And that's not what we expect. Replication is one of those things which has been worked to death across systems. Like people have really, really built robust replication systems. We've done a lot of work on that. You don't expect things to suddenly start breaking in this way. We'll come back to these graphs, but let's take a step back and talk about what's happening here. What really is happening with replication? Now, a lot of you might know replication, when you're running a large-scale distributed search engine, you bring up a lot of servers and replicas which can respond to your search traffic. And anytime you make updates to your index, those updates must be pushed out to all of the replicas so that all of your searchers stay up to date. There are multiple ways to do this. Elasticsearch and then OpenSearch initially had document replication, where every time you get a document, you ingest a document. That document was pushed out to all the replicas. Every replica would index it. So every replica went through the work of creating the data structures that Lucene needs, the index, the segments. And so if you are replicated 100 times over, you're doing the additional work of indexing 100 times over on each of these replicas. But you do get slightly faster near real-time latency because your updates are pushed out to each of these replicas as soon as you get them. Well, updates are not pushed out. Your documents are pushed out to each of these replicas, and then they're locally processing it. It is also complicated because every replica is going at its own pace, and so there's translogs that you have to maintain. And how do you know what document is each replica at? So you need to really maintain some sort of sequence numbers and translogs across them. Then there is segment replication. Segment replication works really well for highly replicated search engines. With segment replication, you have a small set of indexing nodes or an indexing fleet, which is responsible for creating the index. And Lucene has this neat architecture of write once. So every time you index documents, you create immutable segments. These segments are then pushed out to all of your replicas and searchers. So imagine in an OpenSearch cluster, that could mean your primary shards are responsible for doing the indexing, and then the built segments are pushed out to all of the replicas. In our service, we have a similar architecture. We have an indexing fleet, and then we have a remote store where you push this out, and then the remote replicas can pull the built indexes from remote store. Now, with segment replication, again, you can get you get a lot of benefits. Every replica does not need to do indexing work, so that's obviously a win. You get point-in-time restores right out of the box because you know exactly the checkpoint. You can create these checkpoints and you know exactly where each replica is. So you can roll them back to a point. You got a bad deployment up in your indexing pipeline, ingestion pipeline, you know some bad data was indexed. You can roll it back up exactly to that point. In fact, I think when OpenSearch introduced segment replication in 2023, for the highly replicated use cases, they saw 78% improvement in indexing throughput. So any large-scale, highly replicated search engine, segment replication is really the way to go. Now, this is broadly what our architecture with segment replication looks like. We have an indexing fleet, a small fleet, which creates the index and processes all the updates. This fleet is present in some AWS region. Built indexes and segments get pushed to a remote store. The remote store is cross-region replicated, right? So that takes care of your persistence, durability for all of your segments and data. And then each of these replicas pull the updates and the checkpoints periodically from the remote store. And we set that frequency to whatever update frequency we care about. So every n seconds, replicas will pull a replication payload or a checkpoint from the remote store, somehow absorb it, get their searchers onto the latest set of documents, and so all of your updates are in place and applied to your searchers. Your search is then happening on the latest set of documents. Of course, since our search fleet is replicated across regions, one of those regions would be the same as the indexing fleet, but there would be other regions as well. So as we were observing, so I think I have another graph here. This one zooms in to one of those incidents. And you can see, well, it's not that replication payload is exactly fixed every single time. But when the size spikes up, you can see how search latency correlates with it and spikes up. And then you reach the stage where there's just meltdown. There's very high latency. Things are just not able to keep up across your search requests. So what causes these large checkpoints? For a machinery that runs really well, you're getting your updates, pushing them periodically, absorbing them periodically, things you've never seen go bad. What can create large replication payloads? Because if you don't understand that, how do we know what should we fix, what should we avoid? I know this is a busy graph, so stick with me for this one. One of the things we observed was with cross-region replication. Now, no matter how robust our cloud systems get, network issues and failures are a reality that you live with and build around in distributed systems. One of the things we saw is, so if you look at this graph, the dark blue line, which is really spiked up, is the size of your replication payload that was seen by searchers which were present in a different region than the indexing field. Whereas there's another light blue line, it also has spikes, but it has much smaller spikes. Those are the size of payload which were seen by searchers in the same region as the indexing field. And not surprisingly, the pink line here is major faults that were seen by replicas in a different region, whereas the green line is page faults. The light blue line is page faults, the green line is the checkpoint size, but the two spikes at the bottom are the ones for the same region. So something was happening across regions which was causing this problem. When we investigated this further, we realized there can be issues in the replication layer where cross-region copy of your payload can get delayed. And because your searchers are configured, your replicas are configured to pull a checkpoint at a frequency and then refresh on the latest checkpoint, every time once this delay happens, the indexing fleet continues to index its documents, created segments, that gets pushed. But this gets delayed, the searchers and the replicas want to refresh on the latest checkpoint, the latest replication payload. As soon as they absorb it, there's a big difference between the checkpoint which they're at, the snapshot of the index where the replica is at, and the snapshot of the index which it has just absorbed. And that delta is what we see in a checkpoint size. So we're not always downloading and sending the same files over and over. The checkpoint essentially is the difference. It's the payload, the new files which the replicas must absorb. And that led to an increase in the checkpoint size. Now this seems like a problem in the replication layer, and we went ahead, we found some bugs, we solved those problems. But does it only happen if you are replicated across regions? So another thing we observed, and this one is much easier to understand, is that indexing bursts can increase your checkpoint value. So the green line here is your checkpoint size, and the blue line is your indexing rate. Sometimes you can just get a high surge of updates, depending on your ingestion system. And you could throttle that, apply back pressure, but you pay the cost of your data not being fresh enough because you're running a business. You want to apply updates if your system can process it. At the same time, because you're replicating every so often, and replicas are pulling that information every so often, because you have more updates, you just have more data, your checkpoint size, your payload size has gone up. All right, so we can get large replication payloads. You have segment replication, periodically you're pushing it out, you can get large checkpoints. What can we do about it? Can we really make our replicas resilient to this? And as we started digging into this, to understand this better, sorry, did you have a question?
You talked about cross-region replication latency, but your diagram showed the remote store, but there's no relationship between the remote store and the region. It's only the region difference between the indexers and the searchers. So how do we correlate the regional boundaries of the remote store and the searchers?
The remote store internally also has to replicate across regions. So remote store to us, it looks like an abstraction. I just uploaded to an S3 endpoint. Internally, there's a lot that has to go on. The indexing fleet will upload to the data centers within that region, then the remote store has to copy it and propagate that information to other regions, and that's when it will be available to the replicas of a different geographic region to pull it. So even though it's going through the remote store abstraction, just the fact that it is separated by thousands and thousands of miles and across the oceans, there is geographical replication that has to happen at the remote store, which has to be pulled. So yeah, I mean, that's just a complexity which I replaced with a box. Yeah. Anyway, that's a good question. Thanks for actively listening, and we can take more later on. So what I want to dig into now is how does a replication payload get absorbed? So my replicas are downloading the payload, and then somehow my search is using it. What's happening in between? And the magic there happens in something which is known as a searcher manager within Lucene. So Lucene has this object or this class which is called searcher manager. There are reader managers as well. This is a reference counting manager which vends out searcher objects. So what does that mean? So essentially, this class is responsible for creating and maintaining a searcher. A searcher is the Lucene object you use when you're searching. It'll open it on the snapshot of index at that point in time. And then whenever a query comes in, the query will acquire the searcher object from this manager. Internally, your manager will maintain a lot of atomic counters to increase references, to track references on how many queries are using the searcher. And whenever a query completes, it will release the searcher. So a searcher is not killed unless all the queries that are using it have drained out. So there's some safety there. Searcher also exposes an API for refresh. So each time you want to you've made some changes in your index. You don't want to change your index mid-query, right? I mean, if a query is running on a snapshot, it's already computed a bunch of stuff. You don't want to change it mid-query. But for any new query, you want it to start working on include the new snapshot. So that's what this manager lets you do. Refresh, I can understand, is an overloaded term probably for the community, because in OpenSearch indexing, refresh refers to what you call flush in Lucene, which is essentially, this is now a segment will get created. What I'm talking about is refresh on the search side, which just happens under the hood, and a lot of us don't have to care about it. But that's the operation which opens up the searcher and your replica onto the new set of index and segments that are available. So when you do a refresh, it will do an atomic swap. It will keep the old searcher around till the queries have drained out, but any new query starts getting your new searcher. All right. So now what happens when you get a large payload? Searchers are pulling checkpoints at a certain frequency. Suddenly, they download a huge checkpoint. Searcher manager does its job. You call refresh. You have a new searcher available. But the old searcher hasn't died yet. It is still around. It's still got old queries to drain out. But your checkpoint is so huge that your memory is contested now. So instead of being able to load the pages of your new checkpoint, it doesn't fit in the memory you have, and something has to be evicted. Those evictions will evict some pages from your old queries, but the old queries aren't done yet. So the old queries now want those pages back, and suddenly you have thrashing in your system. You continue this for a period of time. Both your new queries and old queries are making slow progress, so you have high latency. You are thrashing on the memory of your system. And this will continue for a while until your queries have drained out, and until your replication checkpoints have stabilized to a size where they no longer need to incur as many page faults, and that's when the issue will resolve. So we do see it auto-resolve, but for a period of time when you run a highly available service, you're running into an issue with your searchers. Yeah.
Just to clarify, the new searcher is created when the old searcher has not, or is still closing?
Yeah, it is still closing. So that's a very good point, and maybe I should double down on that. The old searcher isn't dead yet. Yeah, you've not closed it. you can't wait for it to close because you're constantly getting queries and search traffic. It will, if you keep winding out the old searcher, you'll never be able to, use the new one, which is on the new snapshot of your index. Sorry. So the old searcher, so the searcher manager has done an atomic swap. The new queries will get the new searcher, but the old queries you will wait for the old queries to complete before you kill the old searcher. And those old queries are still underway, right? All right. So now we understand how this works. What can we do about it? Well, the first core insight is cookies are delicious and they go really well with coffee. And then as we think about large replication checkpoints, what you could do is not try to consume the entire checkpoint in one shot. So if you can do something where you allow your searchers and replicas to take small manageable bites, absorb them, and then move on, maybe you don't have to evict as many pages in one shot. Maybe you can give them the lifeline, the graceful timeline to absorb all of these changes without causing an outage in your system. So there are two parts to this. The first one is what we call bite-sized commits. Now, a replication checkpoint was, this one big abstraction that we've been talking about. And initially, the way we'd set it up was, well, actually, I should back up a little bit. Calling something a replication checkpoint is jargon. It is abstraction, right? What does it really mean? So internally within Lucene, every time you do a flush and a sync and a commit in Lucene, Lucene creates new segments and it creates a commit point in the index. That commit point is something which you can load a searcher on, and that defines a point in time on the index at which you can search, essentially, right? Now, the way our system was set up is that every time we wanted to replicate and every time we wanted to push a replication checkpoint out, we would do a commit, create a commit point, and then wrap it up in an object, push it to remote store, pull it, and load it into the searchers. But essentially, there was a single commit which represented the entire checkpoint. What we realized is if we could modify our indexing process so that even though you replicate at the n seconds that you're working with, can you create multiple checkpoints within it? Multiple commit points within it. Commit points that a searcher can look at and either incrementally refresh through all of them or intelligently figure out which ones have the amount of delta in bytes which I can safely absorb. So the first change we did is we started creating multiple commit points. And there are multiple ways you can do it. You can change your indexing strategies accordingly. A simple thing that you can start with is just, if you replicate every n seconds, start creating a Lucene commit every k seconds, where k is more frequent. And then you'll have n by k commit points within your index. Something more intelligent is, can you commit as soon as you've accumulated n bytes within the index? And so each commit is of a fixed size or close to a fixed size. It's not enough to just commit more frequently, because then you're accumulating all of these commit points, and Lucene is intelligent about it, so it does garbage collection. It'll clean up your commits. So you also need to change your index deletion policy. The default on most systems is to only keep the latest commit, because that's enough. That contains all of your changes. You want to change it to keep the last n commits so that they stay in the replication payload when you've pushed it out, right? All right, so our replication payload is not a single blob as long as replicas are concerned. We now have multiple points at which you can refresh. The second change that we make on replicas is called adaptive refresh. So with adaptive refresh, replicas pull the checkpoint. It can look at all the commits. Now you can plug in some strategy which defines what commit point is safe to refresh on or to absorb on. So instead of going directly at the latest commit point, or even the single commit point which it would have done initially, now your searcher, your replica, essentially has a bunch of milestones ahead of it. And it can look at those milestones and decide which one should it absorb. Simple refresh selection strategy could be threshold based. So you know the kind of memory you have. You typically know the size of checkpoint, which is easy to absorb. Let's just create a strategy where we pick the latest commit point, which is below a certain threshold. So you can calculate the difference in bytes between the commit that a searcher is currently on and the commit that it would refresh to. And then if it's below a threshold, just pick the latest commit point that you can absorb within that range. Refresh on it and then repeat. So once you've moved to one commit point, do it again, keep doing it until you are at the latest commit point. So you take a couple more hops. You're not going through all of the commit points that you created because you're jumping based on the threshold that you can absorb. But you're not stressing your system too much should you get a huge checkpoint. We had to make some changes in core Lucene classes to support this. Those changes are merged into open source Lucene now. In fact, they're coming out with the 10.3 release, and I'm also acting as a release manager for it, and I just pushed artifacts out last night or the night before for community vote. So hopefully next week, if builds pass for everyone, we should have 10.3 out, and then OpenSearch and all the systems can start using adaptive refresh right out of the box. All right, so we understand how replication works. We understand how adaptive refresh works. How do we know that we've actually solved the problem? Right? The thing with fixing a ticket is you don't know if it never happened or if you avoided it, prevented it from happening. Right? Of course, you can put a lot of metrics and stuff, but some of the other stuff we did to test it out actually is we created these test simulation environments where we artificially delayed replication. So we would make replication wait for several minutes. Updates would accumulate during that time, so we would always get a huge replication payload, and then we would see how searchers are performing. And so we did those tests that helped us understand the strategy that's working, the problems and remove the wrinkles in our approach. And then when we were convinced that in a dev simulation environment, we don't see any more page faults and latency spikes with this setup, that's where we knew we had solved a problem. During this process, what we also realized is it's not just the act of refreshing on the large payload, but also downloading that payload. So downloads are not free. Even though it's not your Lucene process, even though it's not your Lucene searcher which is doing the download, it's happening in the same container. It's happening on the same operating system. It's competing for the same memory. And we saw that you can't just download a large checkpoint, but then try to do adaptive refresh. You will still incur some cost of major page faults. So what we also implemented is, what we do now is that we look at commit metadata. Now each commit point comes with commit metadata, which is stored in segment infos. So we look at commit metadata, and that tells us exactly the files which a commit refers to. Just going by that metadata information, we can figure out what is the new bytes which each commit is bringing in, and exactly surgically decide these are the commits which are safe for me to refresh on. And then we download all the files for those specific commits. So essentially, we are not just doing adaptive refresh for the searchers, we are also only downloading the files and bytes that we will ever use. And once we put these together, we could see our test environment working well and things solving out. So this is from our test simulation. Again, when you're doing testing, you don't think you'll present it in a talk, so the graphs that you have are things that only you would understand. But I can maybe walk you through some of it. There are page faults, and then the blue lines that you see show you the number of refreshes or the number of hops that our replicas took to absorb the large payload. So this, not each of these lines is very large payload. Some of them are, some of them weren't, but periodically and very frequently we simulated the environment where you're getting a lot of these large checkpoints. And then as you can see the point on the left, so even with our delays and the large checkpoints we looked at, we would max go to maybe 4 hops. So refreshing on 4 commits till we absorb the latest one. And as we did these multiple commit points, we did not see major page faults. The one pink spike that you see, so I'll tell you what happens there. Despite creating the system, you want to have edge cases and fail-safes. So it's possible that none of the commit points in the entire checkpoint payload that you kept were within your threshold. So what do you do then? So we figured if we are storing commits for a period of time, which we think should be enough, but nothing is within the threshold, nothing is safe to absorb, we might as well go to the latest commit point and incur the cost once. So that's an edge case which happens, and this graph shows you that's the point where, the green spot isn't visible, but that shows force select latest commit. So it force selected that commit because that's the edge case you were able to simulate. There was only one commit point for the large payload, and that's where we saw the spike in major page faults that we would have expected. All right, so all of this is fine. Let's talk about OpenSearch. So OpenSearch implemented segment replication 2023. Any system which is doing segment replication, pushing out these checkpoints, absorbing those checkpoints, this is a very real problem that you can run into, especially with highly replicated systems. Now, the system that I've described has been using segment replication since probably 2018 or before. I mean, Michael Froh is here, he had built that system. So he can tell you all the pains of building it. We are just further ahead, and maybe we've seen this. We've run this system for a long time, pushed it to its limits in production for a long time. And so as long as segment replication and the nuances of it go, we've just had more time with those issues. But if you're running a highly replicated search engine and you're using segment replication, these changes, these hooks are for you, essentially. In fact, there was another talk earlier this day where Uber talked about a pull-based mechanism. So Uber, and I think Yupeng, I don't know if he's here, but they blogged about it. They spoke about having invested a lot in changing OpenSearch to allow first for a pull-based architecture, right? And then to work with segment replication and remote stores, and have these Kinesis and Kafka queues which can push, which replicas can use to pull payloads. That's very close to the kind of architecture that we use internally as well. And when you're working with that kind of a system, working with remote store, these are the kind of things you eventually run into. All right, so of course, there's no one size fits all. It's not like these changes will seamlessly apply. And we want to make changes to OpenSearch to bring this in. So I have an RFC open with OpenSearch. We've had some good discussion about the nuances, how it will affect different use cases and workloads there. And now that 10.3 is right around the corner for Lucene, it's much easier for OpenSearch to directly consume it. So we are closer to making these changes and bringing it in, and OpenSearch can start using it. Yeah, well, that's the end of my talk. Thanks for some, interesting questions I got, but I think I have time for more. That's a good question. Life is trade-offs, right? So you have to think about what cost are you paying for keeping this? And since you started with just trade-offs in general, I'll talk about the things which you need to keep in mind. One of them is you'll end up storing more data in your remote store because you're maintaining multiple commit points. Lucene does merges from time to time, so some segments which get merged into new segments, and then these old segments are not required. But because you want to retain commits for a certain point in time, you will keep those around. If you don't keep them around, there's no way you can refresh on an older point in time, right? So it increases the size of your payloads, depending on your window, on how much commits you want to keep and how much merging activity you do. Your mileage will vary, but that's one of the trade-offs of this. The other is, yes, because you do multiple refresh, it does take multiple hops. But I mean, we are a very latency sensitive and an update sensitive operation. And the time increase that we saw in the overall refresh for it to go through multiple hops was negligible. I mean, it will depend upon the tail latency of your queries, because if you just think about it, right, you have two searchers. The old searcher will drain out, and then it will get closed. You'll have a new searcher. Once that is done, then you will refresh on the next commit point. So essentially, if your tail latency is X, that's the time it takes for your old searcher to close. And if you're doing multiple hops, that's essentially the time that will get added to your refresh operation and for your updates to absorb. Usually, I mean, well, I shouldn't say broadly, but for our use case, I mean, we are very latency sensitive, which is why we really care about this and care about search getting affected. So the amount of time we saw an increase for these multiple refreshes to internal refreshes to happen, it was pretty negligible. We could absorb that. Yeah. Yes. Yes. Yes.
Okay.
Yeah. Otherwise, it wouldn't have.
I'm
Yeah.
assuming maybe you had
Oh, I wish. Well, this is your solution to prevent it from happening in the first place. But yes, we are search for Amazon essentially, so we have to have high availability. So we have multiple cells, and then we load shed and route traffic out. That gives the system the time to recover and because it's getting less queries, and then your old searchers can drain out, and you can get the new ones. Yeah. So.
The managed service, the AWS,
Mm-hmm.
does it use segment replication?
I think you have an option to enable it, or is it the default? You have an option to enable it.
If you choose the proper instant types, you get it by default. Yes. They are called OR instant types.
That's recommended for heavily indexed.
High replication, yes, yeah. Otherwise, you do too much work with each replica, right? With document replication. Yes. Okay, I'll correct you slightly there. We chunked the replication payload. We did not split a single segment. What it means is we create multiple commits within Lucene, but we didn't. So a commit, well, a segment is a much more lower level concept for Lucene. Like a commit comprises several segments, and then a replication payload can comprise one commit or several commits. So in our case, the payload comprises several commits, and each commit will have these segments. But I guess if you're trying to, if you're wondering about how do you figure out essentially when should you commit, so I could maybe translate your question to say, how do you chunk your replication payload into these multiple commit points, and then how do you select which ones to absorb? I think you can, so the hooks in open source Lucene that we've added let you define your policies there. So you can add a policy for refresh, and then you can figure out the frequency at which you want to commit. And then if you change the index deletion policy, all of those commit points will get retained, and then you can figure out what to do. But you have to still try it out for your own system and see what works. Like, what frequency are you okay with? How much does it increase your data size, because those are the commits you're keeping? And then how much memory you have, essentially, right? How sensitive you are to these things. Segment-based replication, yes, but that's happening across regions, yes.
Across regions,
Yeah.
which means that the cluster is spanning more than one segment. Am I correct? Or this replication is between two different OpenSearch clusters?
Oh, so I'll have to correct you there. So what I described right now is a Lucene-based search engine, which uses segment replication, but it's not an OpenSearch cluster. It is using all the Lucene fundamentals. It's a Lucene-based search engine, which is using segment replication. And then I talked about how this technology, how these changes apply to OpenSearch, right? But the segments are part of a Lucene index. So every replica, every searcher has to absorb those segments, essentially. They're not split across different clusters. If I was to draw an analogy to maybe try to answer your question better, these would all be part of the same cluster, is what you can see. But yeah, if it was to translate to OpenSearch world, right? Because it's still part of the same search engine. So they're all part of you can think of them as part of the same cluster, right? No, AZs, I mean, you can create them you're creating them in multiple AZs, right, for availability, essentially. Right, yeah. Great, you've been a wonderful audience. Thanks for all the interesting questions. And thanks for coming out, in the afternoon on the last day.